getting darker. It's getting harder to wake up in the morning. But we will persevere. All right, so getting into some really cool territory today. I think one of the most interesting topics that we're actually going to cover is the giant planets, which we'll move into the back half of our discussion today. I think the giant planets are really, really important and exciting because in some sense, they are an interesting missing link between stars and planets. And in order to talk about giant planets and why that even makes sense, we're going to have to look at these things called brown dwarfs, which is hopefully what we will spend the back half of the class doing today, which are traditionally thought of as not quite big enough to turn into stars and not quite small enough to be planets. And so we're going to tear apart that dichotomy and see what sort of substance lies beneath it. But first, we got to talk about Mars today, because we didn't make it to that last week. I know you guys went through that in your textbook and in the assignments and so forth. You've already dealt with Mars, but we're going to talk about it. We're a little bit behind. That's fine. But first, can we talk a little bit just to remind ourselves of what happened last week with regard to, I believe we mostly talked about Venus last week. My friends, tell me something interesting you remember about Venus. Anybody? Yes, Shane.
Well, Venus is constantly going under a lot of volcanic change, and that's why it's kind of to age it by counting craters like we do on moons, because the surface is constantly changing and shifting.
Yeah. So it seems to have a lot of geologic activity, which means it's very difficult to get a grip on the surface. So anybody else, why is the surface so difficult to study in the first place? Anybody? Yeah.
It's the thick atmosphere.
Yeah, it's cloudy. It's super cloudy. Think 100 times the atmospheric pressure, just really gnarly, acidic atmosphere, just really, really rough. And I think that the longest spacecraft have been able to hang around for a little more than 20 minutes. And so they're trying to change that. There's a new program that NASA is undertaking to get back there by around 2030, and they're hoping to hang around for, I think a number of hours at least. They're going to descend very slowly and take a number of readings along the way and take some pictures and maybe even drill down a little bit. So that'll be interesting. What else? We didn't really get into,
I just talked about Venus.
Yeah. What else do you remember?
Orbit. I mean, not the orbit, but the path out goes.
The rotation.
Yeah, I like the rotation too, because its rotation's longer than its days longer than its year.
Yes. Yeah. That's very, very strange. We probably won't see that again. It also goes the wrong direction too, which is very, very bizarre. I had this. I'll share this conversation with you guys whenever we publish it. But I had this incredible conversation with this astrophysicist yesterday for the podcast, and he essentially what his job is. It's a really cool job, and I think he only gets away with this because he's in France, and they don't have to. They have a very different funding structure than the universities in the United States. And in France, the government pays for all the science, as opposed to in the United States, you basically have to say why your science is going to be technologically useful. But what this guy does is he basically sets up these computer simulations where he builds different solar systems and sees what would happen. Like what if you move the Earth a little bit this way or a little bit that way? And we were just exploring all the possible ways that Venus could have ended up so strange, because in some sense he has this really creative job where he just imagines these crazy scenarios that could have lent itself to to these strange dynamics. Because Venus doesn't, like we keep coming back to, and I think this is what makes this course, or makes this planetary science, solar system astronomy really, really interesting, is that the story that we've been telling for the past 300 years is in some sense really antiquated. And so that story is due for a good update. And Venus is one of those players that really just makes you scratch your head, because it doesn't really make a lot of sense in the traditional way that these planets form, where they were at 4 billion years ago and 4.5 billion, whatever. And they've kind of just been hanging out there, changing a little bit, but not much. Venus is very, very strange. And so, one of the things that this gentleman, I'm blanking on his name. His name is Sean. anyways, I'll share it to you guys eventually. One of the things he pointed out was that if planets have moons that depart from them, you can get really interesting dynamics as a result of it. So if Venus originally had some big, chunky moon like we did, perhaps if that was stripped away by some process, that it could have, radically altered its dynamics in some sense. The same way that, we were talking, he was working with a science fiction author, and the science fiction author wanted to tell the story of how the Earth left its orbit. And he came to Sean and said, is this scientifically possible? Like, what would lead the Earth to leave its orbit? And if it left its orbit, could it survive long enough to join another orbit? And so Sean did all the simulations, and he was like, yeah, it's possible. And one of the easiest ways for that to happen would be if it had more moons. And so when it got, maybe a passing star came by the solar system and jostled the gravitational dynamics. And then when it got to the new solar system, it essentially, it used some of that extra momentum that it had with its extra moon and donated the moon. The moon flung off, but that kind of braked. It added brakes onto the orbit of the Earth as it stabilized into the new solar system, which I thought was really interesting. So these are, of course, like really, really unlikely events. But I think the unlikely events are really interesting to ponder because the fact that we're all just sitting here having this conversation is an extremely unlikely event. If you just try to calculate what are the odds of this happening, it seems like they're near zero, but here we are. So rare things do seem to happen, which is very, very strange about our own existence. All right. Anything else interesting? I wanted to mention some of the cool more technological ideas people had about Venus. I didn't really get to it. One interesting thing is that if you go high enough, so people have been thinking, is Venus some place we could ever see ourselves inhabiting in any degree? And you might think, nah, that's ridiculous. It's too hot and pressurized, and it's an awful place to live, basically. But there's a proposal on the table that actually, if you go really high up in Venus's atmosphere, there's a point, I said Venus's atmosphere is something like 100 times our atmospheric pressure. But if you go up high enough, there is a layer at the top that's about the same pressure as our atmosphere. Now, if you could set up some sort of a floating station up there, you could actually, in some sense, imagine it floating, resting with buoyancy on top of that really thick atmosphere. The cool thing is that you could at once have a station that was orbiting the planet, and so it could experience day and night at its own rate, which would be comfortable for human beings, essentially, because like we said, Venus its day lasts longer than its year, and so you wouldn't want to hang out in the sun for hundreds of Earth days in a row. And so if you were able to have this sort of orbiting, floating base up above the clouds, you might find yourself in a comfortable situation to actually study the planet, which is, I can see that happening. So, all right. Any more thoughts about Venus? Now, so these are one last little comparison of the two. I guess the other really important thing we got to remember about Venus is that it's another strange piece of this story, which has yet to be explained, is that Venus, by all accounts, is compositionally very similar to Earth, and it has a lot of geologic activity, and yet it doesn't have a magnetic field, which is very perplexing. It has the same density as the Earth, more or less. I think it's a little bit less, but it's very, very close. And so one of the reasons why we think Earth is so dense is because it has this really thick, solid core at the center, which aids its density. And of course, the core is important in stabilizing our magnetic field and so forth. The other component of that magnetic field we've talked about is having the ability to circulate some of this inner core liquidous stuff, this magnetizable conductive material, right? And it seems like there's a lot of convection on Venus too, so this is really, really perplexing, and we don't totally understand that. So that's really, really strange, and you can see they're very, very different. Look, obviously, Earth and Venus are very, very different looking. This one's lacking the atmosphere. This is done with radar imaging. And then we talked about the moon before. Now we're going to talk about Mars. Mars is actually quite a bit smaller than you probably have come to understand, which is probably the first thing to take note about it. I'm going to skip through this. So Mars is, I think it's got something like a third of the gravity of Earth, which is something you don't really see much when you, on these movies, you've seen these sci-fi movies about Mars, or maybe you see The Martian or anything like this. You don't really, they don't really play up the fact that, that you'd be quite bouncy on Mars, just like on the moon. It's got a little bit more gravity than the moon, but not a lot. So it's a pretty tiny planet, actually, despite being, and it's less dense than the Earth by quite a bit as well. So that's interesting. We'll talk a little bit about the mythology associated with it, not as in depth as Venus, but needless to say, Mars is named for the Roman god of war, which is quite interesting. I mean, it's interesting that the color red has been associated with war and rage and anger. The seeing red and so forth is just kind of inherently baked into the cake of so many different cultures. And I can't think of a great reason for that other than blood, which seems like that might be a sufficient answer to the question. But for whatever reason, and we'll talk more about the different cultural interpretations of it, but it's always been associated with rage and war and these sort of violent passions, which makes sense. Has anybody seen Mars in the sky before? It's pretty obviously red, right? It's if you want to see Mars in the sky, you probably can most of the time, and it is that red star, for lack of a better word, that you'll see in the sky. So people have been watching it for a really long time. I think one of the questions we want to ask ourselves today as we look at Mars is, why are people so interested in it, right? Elon Musk is absolutely dead set on getting people over there and setting up colonies and so forth. And that's an interesting question. Like, is that a good idea? Is that really is it necessary to do that? Or is the moon a better place in terms of branching out? If we assume, as we did previously, I made the case to you that I think a lot of this space exploration is in the long-term vision associated with something like finding a new world for ourselves. Is Mars a good stepping stone for that? And of course, Elon's made a case that it is, but there's also a lot of really dystopian sci-fi about what it looks like to live on Mars. Anybody see The Expanse? No? Oh, God, that one's good. You guys should watch some of that, at least the first 2 seasons of The Expanse. It kind of takes on this idea that humans have branched out into and it's also a book, a novel series, if you prefer to read. But it takes on the idea that humans in the future have started mining asteroids, which it seems like we're going to do. And they've set up this colony on Mars, which it seems like we're going to do. And the result of this is a little bit catastrophic, because what happens is that Earth becomes a sort of garden paradise for the very wealthy, and the sort of huddled masses are sent off to the colonies, essentially, which has some precedent in antiquity. It's quite interesting, A lot of people who came to this continent from Europe were in some sense of fleeing privation and poverty and persecution. And so this kind of plays out in The Expanse. It's a really interesting, it kind of goes super deep sci-fi towards the back half of the show with aliens and wormholes and everything. But the first part's really, really quite fascinating because it looks at the way that these are serious issues that we'll have to face when we go and colonize and it's definitely going to happen when we start spreading out throughout the solar system. It's there's no place like home, right? It's going to be very difficult to find a place that's actually comfortable out there without some serious innovation and probably a lot of money poured into it. Right now, if we were to go to Mars, the talk is something like we're going to have to hang out in these caves because the radiation is so bad there. It's got no magnetic field. It's got no the atmosphere is really, really thin. And so who here wants to go and live in a cave for the rest of your life, It's not particularly appealing. And so who are the people who are going to end up doing that? Well, in some sense, they'll be the explorers and pioneers, but staffing a city-sized or a colony is going to take a lot of hard labor by people. And so, I don't know, it's a really interesting social dynamic to try to navigate, to imagine the future of. So let's keep that in the back of our head as we talk about these different explorations of Mars and why we're so interested in it, because it seems like there's at least some portion of humanity. I keep pointing at Elon Musk because he's the most vocal. He's got the most money to throw at it. But why do people want to go to Mars so bad? It's very interesting. And I think that we'll find that that's rooted in a very recent conception that Mars was a habitable place. So all the way up until 1965, when we put an actual lander on Mars, people were pretty darn convinced that it was habitable, right? And we'll see why that is. But if you look at the thing, it kind of looks like it has some ice caps. These dark, blotchy things were really, really convincing to people for most of history that there was something biotic, some sort of plant matter or bacteria or something. Actually, these dark patches come and go with the seasons, which is even more interesting. And actually, the debate continues in some sense to this day. There's been some really interesting findings in the different landers that have been there that kind of point to biotic processes that could still be going on. There's a seasonal variation in methane, which is traditionally thought of as an organic substance produced by life forms. Now, there are abiotic processes that can accomplish that, but there's a few other things, which we'll get to that in a minute. So let's make sure we are acquainted with this thing as a body in the solar system first. So let's see. It's about 250 million kilometers from the sun. That's about, let's say, we're 1 AU from the sun. That's like 1.6 AU from the sun, so it's a bit further away, which means that its year is a bit longer as well than ours. But interestingly, the length of its day is almost identical to the length of the day on Earth, which is very strange. We don't see that anywhere else in the solar system. It also has an almost identical tilt to the Earth, right? It's axial tilt, which gives it its seasonality. That's why the seasons on Mars seem to parallel our seasons in such an interesting way. Like I said, there's these seasonal variations. The ice caps shrink and expand and so forth, and you have this darkening of the surface, which is very, very perplexing. And all of this fed into, I think, why people became so fascinated with Mars as a potential habitation. I mean, wouldn't it be nice if we could just go to our next neighbor and branch out, as opposed to having to travel to an entirely new solar system? I mean, that's a really wonderful dream. But I think, unfortunately, what we're finding more and more is that Mars is much closer to a barren hellscape than a habitable place. And so maybe those dreams are a bit misfounded. You couldn't, there's lots of there's terraforming ideas. We'll explore that a little bit, because I think that you could make an atmosphere on it, right? It's not inconceivable that you could make an atmosphere. There's water available, we think, in the polar ice caps below a thick layer of dry ice, essentially carbon dioxide ice. There is water. There's carbon sources, right? And there's methane. There's this CO2 dry ice, which, of course, plants breathe CO2 and they make oxygen. That'd be really nice. We could probably figure something out. The big problem is that why do we even still have an atmosphere? Well, it's because we have that magnetic field that shields us. The solar wind is devastating, so it rips away the atmosphere. And even our atmosphere is getting lost appreciably every year. We're losing lots of material. But Mars without the magnetic field has lost almost all of its atmosphere, by the time we started looking at it. And so the question is, even if we were able to generate an atmosphere on Mars, how do we keep it? And there's some interesting proposals for generating an artificial magnetic field, including which actually don't seem as sci-fi as it sounds on first base. So the basic idea is that you put an orbiter in place that was able to essentially travel around the thing and produce some sort of really strong magnetic field. Maybe even attach it to one of the moons. So we'll see that Mars has a couple of little baby moons, and we could use one of those maybe as the base for that. Yeah, that's the thought. But those are a little bit, pipe dreams right now. They haven't really been developed fully. But they seem, a lot of times when you read these kind of far out visions for for terraforming and so forth, some of them seem like they have more promise than others. And that one I was quite surprised to find seemed at least practicable. It seemed theoretically possible in a way that a lot of these projects seem too expensive or too elaborate or too many steps to go wrong. So that's something to read about. You can read about that. I believe there's a Wikipedia article on it. There's a few blogs you can probably check out if you want to learn more. All right. What else are we going to say about this thing? In terms of, again, why doesn't it have this magnetic field? Well, there is some evidence that it's been magnetized in the past, and it's hard to say why that is exactly. Of course, it has a very metallic-rich, iron, nickel-rich crust and body, and so it could be magnetized. Particularly, if it spent some, there's a few ideas. Maybe it had a solid core that stabilized it. Maybe it had that liquid layer that cooled over time. There's definitely evidence for volcanism on the surface of Mars. Actually, the biggest volcano in the solar system is on Mars. We'll talk about that. So in the past, it may have had this kind of convection necessary. It may have had a liquid layer above the core that was capable of generating magnetic field. Maybe it spent some time near a really highly magnetic body that magnetized it too at some point. That's just pure speculation, but maybe it spent some time near a sun in a way that it got it magnetized. So of course, stars are extraordinarily electromagnetically active bodies. So I don't know, but there's some argument against that too, because the density is actually really low compared to Earth, and again, and compared to Venus. And of course, the presence of that solid core in some sense enables us to explain our own density. Remember, we're on the most dense rock in this entire solar system, which by itself is a very perplexing matter. The fact that the most dense stuff didn't end up in the center of the solar system inside of the sun is in some sense a really interesting mystery. But Mars isn't that dense. So Earth's density is, I think, 5.5 grams per centimeter. Mars is something like almost 4. So it's quite a bit less dense, and so that might not provide for this similar mechanism. Maybe it wasn't able to ever really sustain that magnetic field. So whatever it had was rapidly lost in terms of atmosphere and so forth. And of course, the atmosphere is continually generated on our planet. A great contributor to our atmosphere is volcanoes, right? They dump a ton of water vapor and gas. Carbon dioxide into the atmosphere, right? They're very, very strong contributors to atmosphere. So there may have been a point where Mars was volcanically active and it had something like an atmosphere, but it was very quickly washed away by the solar wind. All right. So these are the orbits, just to give you a bit of a sense of how this goes. Mars is, of course, going kind of slowly. And, this again, these particular dynamics are, in some sense, what confused the heck out of the ancients and led to that geocentric worldview, because Mars appears to go backwards right as we pass it. We've talked about this. This is really, really critical in the argument about where Earth was in the solar system and these wandering stars, what was going on with them. So Mars goes much slower, so it takes almost 2 Earth years, 780 days about, to go around the sun. So that's very different. But despite that, it has a similar day and a similar seasonal tilt to us, axial tilt. So in terms of Mars's moons, this is the Earth, this is the moon, and you probably cannot see Mars's moons in comparison because they are that small with respect to our own moon. And these moons are actually really, really interesting. So they're called Phobos and Deimos. And here's a little picture of those moons as they wander around. And, what's really interesting about, so of course Phobos and Deimos are named for these deities, these Roman deities of rage and so forth once again. But they're very, very strange. So one of the moons, the smaller of the two, is called Deimos. Deimos is actually escaping from Mars, so it will not be there for very long. It's really small. It's about 4 miles across. Yeah, Really, really small. The larger of the two is not even twice that, though. It's only 7 miles in diameter. That's Phobos. And Phobos is actually so close to Mars that it's falling onto Mars, and it will eventually crash into Mars. And so both of these moons seem to be, in some sense, slated for termination in their own various ways. So I believe that guy on the outside is going to be Jupiter.
Okay.
Yep.
What's how the moons changed so much on that second picture? It looks like they're
I
going
think
around
it's
the
just
sun,
I think it's just zooming in on them.
Okay. All right.
Yeah. Sorry, that's a bit confusing. I probably found a better GIF than that. All right, so these moons are also really strange. They honestly kind of resemble asteroids more than moons. And they've been, in particular, Phobos, we'll zoom in on it. It actually looks more like a pile of junk that's kind of glued together with this thin patina, a roasted patina on the outside. It's like if you took a bunch of rocks and cooked them in a furnace or something, which is very strange. It actually doesn't even seem like the things are big enough to be held together by gravity. So in terms of their origin, there's a lot of interesting speculation about that. Was it a big chunk of, and honestly, it's particularly Phobos looks a lot like the material from Mars. It's very similar in composition. It looks like a little baby chunk of Mars. So was it in some sense scattered off of Mars? There's one of the biggest impact craters that we know of in the solar system is in the northern hemisphere of Mars. It's huge. And so was Mars just smashed into by a Pluto-sized planet at some point that liberated these chunks off of it, which eventually became moons? I mean, that's probably the most logical assumption. It's very unlikely, in other words, that these moons formed in place. They're just not big enough to have accreted, right? It'd be very hard to imagine pulling together a bunch of these pebbles and so forth under gravity alone. They're just not big enough, which is really interesting. All right. Oh yeah, let's take a little closer look at this thing. This is actually, it kind of looks like a CGI, but this is apparently imaged by the Mars Reconnaissance Orbiter. I imagine that they false colored it afterwards. But it's you can see this thin patina on top of it, right? It's sort of smoothed over. But the density scans of it, the penetrating radars that they've used have showed that it's basically just a bunch of bricks all squished together. Very interesting. The gravity is so weak, so, if you're, say, a 150-pound man, which a few of you are anyways, you'd weigh 2 ounces on Phobos, okay? So it's just doesn't have enough mass to pull itself together. Mm-hmm. Yeah, I mean, mass is in its most pristine form, mass is just a quantitation of gravity. Yeah. And inertia, which seem to be the same basic idea. That opens a huge can of worms, though, so we won't go into that too much. When we start talking about mass in terms, you opened the can of worms. I can't stop now. So when we talk about mass, throughout most of the history of science, people were talking about mass in terms of gravity and inertia, the ability to get something moving, which is related to gravity. They're kind of identical, just two sides of the same coin. But in recent times, people have started using the word mass to talk about subatomic interactions. But what they're really doing is they're taking the, let's say, electromagnetic force necessary to deflect those particles, and they're converting it into mass units. So it's almost like it's an effective mass. It's not a true mass in that sense. It's like an equivalent amount of effort necessary. Yeah, so I wish they didn't use that word mass for subatomic stuff because it's not totally appropriate. It's more of like a mass equivalent. But so you'll hear about the mass of the electron and the mass of the proton and stuff, and it's not quite appropriate, I think. It's not quite the right word to use. Because mass seems to have been invented in order to quantify gravitational and inertial effects, which seems to be an atomic phenomenon. It's what atoms do to each other. They seem to pull on one another somehow. Okay, what else did I want to say about this thing? So Phobos, like I said, it's actually been, in addition to maybe being a place that we could park that magnetic field generator in the deep future, It's also, in the immediate sense, a really attractive candidate for an outpost, right? For a way station on the way to Mars, right? So one of the nice things about it is that, it doesn't have much gravity, right? So it's very easy to land on and to depart from with very little effort. It would be a really nice place to basically set up a station to go down to Mars periodically and then come back to. You could send little robotic orbiters down from it, fly your main base out to Phobos, which is in orbit already. You could be stationed there. There's also this idea that you could pick up some of the dust on the thing and sort of use it as a brake for your little robotic orbiters, or your robotic landers. So what you do, basically fill up sandbags with some of this rubble, and then as you're landing, you sort of eject it out in front of you, and it burns up in the entry and breaks the spacecraft as it lands. So that's one of the more salient proposals for how that would work, which is interesting. So I would expect to see Phobos being used in some sense technologically as people insist on exploring Mars and potentially inhabiting it in the future. So let's see. Like I said, the first time we went there, landed on it, was a US NASA-based project. This was Mariner 4 in 1965. We started getting images transmitted by the Viking lander. That was about a decade later, 76. And then, since then, the United States has really been the only other people there. The Chinese also, in 2021, put a lander on board, which is the Zhurong lander. And then the mission that's underway right now is interesting because what they're doing is they're collecting all these samples in vials. And they don't have a way to get them back to the Earth right now, which is really interesting. And the plan is that they will eventually figure out how to get them back to Earth. And when they do, they'll have all of these samples ready to go. And that's some really interesting long-distance thinking. And there's a couple of proposals of how to do that. So I think that the best idea is something like you send these robotic craft down that have little rockets on them, and you load the samples up into the rockets and shoot them back to Earth. Now, that seems like all well and good, but there is a pretty serious danger inherent in sending things back to Earth. Why is that? Well, not only, but what's that? It has to land safely, but why wouldn't you want to bring stuff back from Mars to Earth? Exactly, yeah. So again, this idea of whether there's biotic substances on Earth, that is to say, not big green men, but little green men. If there's bacteria or anything, primordial life forms of any sort on Mars, the jury's a little bit still out on that. I would probably tend to say there isn't, but what if there is the real question. We saw what let's say a somewhat innocuous respiratory virus did to the world for the last 3 years. Imagine what a really nasty thing that had nothing in common with our own biology could do to just the economy and just social stability on Earth. I mean, it could be really, really bad. It would probably take us much longer to figure out how to address a pathogen from another world than it would for us to address a new pathogen on our own planet. At least we have some similarities, at least we knew what coronaviruses were, right? At least we had some basic biology that could help us understand them and develop some, at least intermittently effective treatments for it. But I think it would be a complete disaster. So there's a pretty vocal majority, and I think this is in some sense the reason why we're collecting all those vials and we haven't sent them back yet. I really doubt that it's because we don't know how to exactly. I think that it wouldn't be that hard to send them back. I just think that there's a lot of trepidation about whether that's even a good idea in the first place. There's some really interesting anomalous data too concerning when they brought rocks back from the moon. I mean, they found little staph bacteria on some of these samples that they brought back from the moon. And most people said, well, those got contaminated from the spacecraft itself, which already had the bacteria, let's say. Which is probably true, but they did go to extraordinary efforts to sterilize those spacecraft, and of course they had to go through the atmospheric reentry and everything, so I don't know. The jury is still out on whether there's microbes out there, but one thing that we can learn from that lunar landing escapade is that it does seem like the bacteria can survive reentry. They can get back here. And so bringing things back from Mars is something we haven't done yet. We haven't brought a spacecraft back either. And it's going to be a very careful and difficultly weighed decision.
I saw on the news that we lost contact with our rover on Mars for a couple of days because we're lined up with the sun.
That makes sense. Yeah, that rover, the most recent rover, with the helicopter module and so forth, pretty cool stuff. It actually lasted way longer than they thought it would. And I think that what the plan is they're basically going to keep the thing alive indefinitely. It has, I guess, enough. It's got solar sails of some sort. And they're going to be able to keep transmitting data back periodically. They'll just turn it off for weeks at a time and then check in on it every once in a while. We sent these modules clear outside of the solar system that we were absolutely not expecting would be able to keep talking to us, and they're still talking to us. So this is cool. This is actually a good sign that we're, in some sense, over-engineering these things to the point that they're still useful to us long after they were supposed to be. But there's definitely all sorts of return to Mars enthusiasm. I haven't been too involved in the NASA conversation in a couple of years, but when I was really involved in talking to a lot of people working at NASA maybe 3 or 4 years ago, it was the absolute biggest topic on the map. Everybody was working on Mars and how to get to Mars and how to study Mars and life on Mars and all of this about Mars. The moon seems to have taken the spotlight for the moment, and I think that there's in some sense good reason for that. It's much closer to us. It's not like I opened up this talk at the beginning. You go to Mars, it's like 6 months away, right? You're stuck there. Like you're going to be there for a long time. And people don't do well in isolation. They don't do well in space. Even the 6-month journey itself is really dangerous. The amount of radiation you'd be exposed to on that journey is incredible. And then you just talk about taking people away from their planet for years and years. It's a really hard bargain to push on somebody. And the moon, in some sense, is much easier. We can travel there in a week or so, spend some time, come home. You can rotate the crews out on the moon. It's in some sense a much smarter proposition as far as I'm concerned. At least in terms of working out all of these real questions, like the psychological questions, the biological questions. How dangerous is it to live in space? We don't really know because almost all of the astronauts that we have in space right now, they're on this orbiting ISS, right? It's inside of the protective zone of the magnetic field. It's before the Van Allen radiation belt where things start to get really gnarly. So it's in some sense, these people are shielded from a lot of the biological problems that you would expect. Now they do get more radiation than we would down on the ground level, but it's still a lot safer. When you get out on the moon, you get out on that travel to Mars, it's going to be really, really dangerous. So it makes sense you want to work those things out on the moon first. At least you can limit people's exposure to these things and in some sense just work out the psychology of it. I think I talked to you guys a little bit about the Biosphere 2 project in the desert out there in Arizona where they tried to lock themselves inside of this habitable, self-contained world. They tried to do it, I think, for 5 years. I think they made it 1.5 or something. And a lot of the problems that happened were not technological, although there were some technological problems, but the problems were people turning on each other and just doing all of the treacherous things humans do to one another when they're locked in a room together. So there's a lot to be sorted out, I think, before we start reaching out, even as far as Mars, let alone to other solar systems. So maybe it'll make a good test case in the future once we work things out on the moon, but I'm not sure about in the immediate sense. So one of the really nice things that's made Mars so easy to observe here on Earth is that the eccentricity, let's say how much of an ellipse it is, actually happens to line up really nicely with Earth when it's at its closest point to the sun. So when we're both close to the sun, we can see Mars really, really well. And so that's something to pay attention to if you're tracking the skies, is when we're both at this perihelion position, right, which means closest to the sun, we can see Mars really, really well. And I think that that's led to this long history of observing the surface of the thing. And people have been doing that forever. The Sumerians talked about Mars. They watched this thing. Of course, even the Sumerians associated it with, it was the god of war and plague, which is really interesting. That red color, again, just associated with strong emotions, passion, anger. It's just this universal sign of strength and power and courage and danger. What else do we have to say about these guys? The Egyptians were also very, very much aware of Mars, very much tracking it. The astronomers were tracking it. Again, they associated it with the same sort of spirits and deities. Ancient Greeks came along and called it Pyros, which is the god of fire and death. It didn't really start to be treated as a material body until quite late, and that really came down to the telescope. And so one of the first people to build a telescope and actually look at Mars properly was Christian Huygens, who we talked about, came up with, really refined and came up with the wave theory of light. This guy was just a complete super boss. I think he's one of the biggest superstars in the entire history of science as far as I'm concerned. But he built this kind of ridiculous telescope, which you can see here. He essentially put the lens up in a tree or like up on this telephone pole so that he could have a long enough focal length to actually observe the thing. He also was the first guy to discover the rings of Saturn, which is pretty cool. And what Huygens did was he started to draw these pictures of Mars that nobody had ever seen before, including these dark patches that changed with the seasons. And this, I think, really, really started to captivate people's imaginations. A couple hundred years later, telescopes got even better. And this guy named Schiaparelli used this 22-centimeter telescope over there in Italy, in Milan, and made these really detailed maps of Mars. And one of the things that Schiaparelli found out was that there seemed to be canals on Mars, these very straight-lined features, almost like highways. So as you can imagine, this absolutely took off. And, this was not some antiquated idea. I don't have the date under when he made these observations, but I imagine it was somewhere in the 19th century. And that idea persisted all the way up until 1965 when we actually touched down on Mars, right? And when we touched down on the place, it revealed the pictures that we eventually got back and the samples that we got back just kind of put the nail in the coffin on that idea, because we saw this really barren landscape, this really thin atmosphere. There wasn't pools of water everywhere. It didn't seem habitable for the first time, and people started to look for alternative explanations for these cracked-like features of Mars that weren't an alien civilization of Martians. But the fact that idea persisted so long really makes sense, I think, in terms of our persistent fascination with Mars. In some sense, a lot of the early UFO culture and everything was still centered around the idea that Martians were a real thing, and they were, potentially people over there that we could communicate with. And perhaps the UFO phenomenon really took off, particularly after the Second World War, which was well before we'd actually been to Mars still. And so that idea was alive and well. There's, of course, the War of the Worlds fiasco. Do you guys know about that? Which is pretty crazy. So there's this radio play that was read about Martians invading. It's actually quite an entertaining listen if you get a chance. It's very short. But there was a radio play that was dramatized, and people who tuned into the radio, they didn't necessarily get the preface that this was a drama, and they thought it was really happening. They thought the Martians were actually invading, and it led to all sorts of pandemonium. I don't know what year that was. I want to say in the 30s, maybe. But again, from a scientific standpoint, it was completely reasonable to those people at the time. And that wasn't that long ago. That's what's really, really, really crazy about that. I think we can't ignore that in terms of why we're so interested in Mars still at this point. So, 1965, the first real publication came out denying, the possibility that Martians were a thing. It was this textbook, a source book on space sciences, and the chapter on that read, although there is no unanimous opinion concerning the existence of the canals, most astronomers would probably agree now that there are apparently linear, markings, perhaps 40 to 160 kilometers or more across considerable length. But they'd moved away from thinking that these canals were anything biotic for the first time. So that was in the 60s. Really, really crazy. Okay. Let's see what else we have to say about this thing. I want to make sure I save some time for brown dwarfs today. So Mars is about half the diameter of Earth. It's much less dense than Earth, so it has about 15% of Earth's volume and 11% of Earth's mass, which is really, really interesting. And that gives it 38% of Earth's surface gravity. The composition is more or less the same. We talked about that. It's a little bit lighter, so the iron sulfide and iron and nickel is thought to contain a lot more light elements than Earth's crust. So of course, or Earth's mantle. So Earth's body, let's say, is much more metallic in some sense than Mars is. And that's thought to account for the density differences. What else do we want to say? It doesn't seem to have this nice liquidy layer below the crust that we do, which gives rise to our tectonics. So that's a key difference. Now, when we start to look at the surface of Mars, it's very, very unique amongst all of the different bodies that we're going to look at in the solar system. The northern hemisphere is wildly different than the southern hemisphere. You guys have a question back there? Sorry, I just heard you. I thought you said something. If you look at these things, the top is completely scathed of any impact craters. And so you can't really see it on this, but in the northern hemisphere, it's thought that there's evidence of an enormous impact crater of something the size of a Pluto-shaped body that maybe leveled all of this and completely washed out the craters that were present on that thing. So there's a really interesting history going on here that's not entirely understood, but we have two very different appearances. You know, it's kind of like the moon, right, where we have parts of it that are completely pockmarked in craters, and then we have these maria that are more or less devoid. They have a few impact craters, but very few. And the question becomes, why is that? You know, on the moon, it's attributed to volcanism because of this basaltic flow dynamics that they apprehend. But up here, we don't see that as much. Actually, the more volcanic regions are down here in the south. You see this plain over here with these three volcanoes, and then the really big one, which is called Olympus Mons. And so all of this is thought to be from volcanic flow. The north, not so much. And so it's a bit of a mystery how that went down. I want to show you guys something else that's really, really interesting. This is that volcano, Olympus Mons, which is really interesting. It's actually something like, if you really count it from the seafloor, whatever would be the seafloor equivalent on Mars, it's about 3 times the height of Mount Everest. So it's enormous. It's by far the largest mountain in the solar system, or the largest volcano. I'm going to come back to this in a second because I want to show you guys something really interesting. One of the most interesting features on Mars is this huge gash in the side of the thing. And this, I think, is, in my opinion, one of the most wild mysteries on all of Mars. So the current thinking is that this gash appeared because as Mars cooled, it sort of fractured. It sort of just crumbled and broke. This happens, of course, with roads in the wintertime and so forth, right, as well. But it's, I don't know. It's very strange. It looks as if somebody just dragged a fingernail across Mars, right? And so there's not a very good consensus picture on in any way that could have been done by another body, but it certainly seems like it could have been, right? Seems like it might have had a close encounter with somebody else, which is very, very strange. Of course, if you look at the elevation radar, you can kind of see how it's like a real serious canyon across that basaltic field. So it must have happened after those volcanoes erupted and left all of their magma plains in the wake. Very, very strange. All right, we'll come back to that in a second because I want to think about some different things here. What could have led to that? Another reason that I think Mars is a bit unattractive is because its soil is really, really nasty. So in order to grow plants, you need good soil, right? The soil is really salty there. And maybe you've heard the term salt the earth, right? One of the quickest ways to destroy somebody's field is to salt it. Not only is it salty, but it contains this particular salt called perchlorate, perchlorate's actually really toxic to human beings. It's really nasty stuff. So, just wandering around on this place, tracking dust into the spaceship, it's bad news. This is poisonous stuff. And again, all the more reason I'm not sure that Mars is that attractive of a place to set up a base. It does seem to have water, though. So that's nice. And of course, we know we need water to be able to build rocket fuel, to be able to explore further. So there is some hope that, it's potentially a good waypoint in order to refuel and move outward even further. Now, the problem is that dry ice covers almost all of the liquid water, which is found at the poles. So there's a really thick layer. Let's see here. I don't have the stat on that. These are the two different poles that you see here. Let me see here. Okay, so it's covered in about 2 meters of dry ice. And that dry ice cycles and leads to, seasonally leads to some of that carbon dioxide being evaporated into the atmosphere. So we have to drill down if we're going to find it. And I think some of the hope is that some of these future rover projects, and I think this is in some sense why they wanted to get these robotic devices up and running, is so they'll be able to drive from the nice landing spots, which are lower down in latitude. They'll be able to drive up there to the North Pole or to the South Pole and drill down and receive some of that water. But it's thought that there's a really decent amount of water available there. I had an interesting stat here about this. It seems like that if the water in the South Pole was melted, it would be enough to cover the entire planet up to 36 feet with water. This is a good amount. All right. There's also been off and on arguments that there's water seeping through the surface of Mars, and this is a false colored image of some of that potential outflow. They call these outflow channels. These are debatable. People argue to the present in the literature about whether or not these represent actual water. And a huge reason for that is because people don't have a great way. Mars is covered in these really dendritic channels. Does the word dendritic make sense to you all? So dendritic comes from the root for tree, right? So it's this branching pattern of fractality. And you see this in rivers, right? If you look at rivers, they kind of branch, right? All these little feeders give into the main channel, which then flows out to the sea. And so Mars has a lot of these dendritic etchings on the surface. It has a lot of what look like waterways. The problem is that we can't detect this water, and we can't see necessarily that all of these channels have obvious inlets and outlets. So on Earth, almost all of our inlets come from the mountains, right? The snow melts, it feeds down into the valleys, and they flow out to the sea. This doesn't seem to be necessarily the case on Mars. The best example was that huge gash that I showed you guys. This huge canyon, the Valles Marineris. Well, that doesn't have an inlet or an outlet at all. It doesn't seem to be topographically aligned to any mountain that would feed into it. So it doesn't seem reasonable that it could have been carved by water at all. And so what's carving these if not water? And there isn't a good answer for that. I do think there's one thing I wanted to show you guys which is really interesting. If you have the opportunity to, say, hook up, to drive a huge current through the surface of a material, you can also get this really cool fractal pattern that gets out of it as well. So something approximating ridiculous amounts of lightning also seems to be capable of generating these patterns. And I'm not saying that's what happened on Mars. I'm just saying that, and I have no idea what in the world would lead to that kind of a discharge, but it does seem to be capable of reproducing the same pattern, which is quite interesting. All right. We'd have to zoom in closer to see these on Mars, and I'm sorry I didn't bring you a picture of that. Maybe we can see some stuff. You can see some of these little rivulets over here up to the upper left-hand corner, particularly over on, your guys' left over here. At the far left, you see more of these dendritic rivulets. All right, what else do we want to say? The atmosphere. The atmosphere is abysmal, so the surface pressure is about 0.6% of our own, which means that there ain't much atmosphere, and most of it is carbon dioxide. So does anybody remember how much carbon dioxide by percentage we have here on Earth? per million, yeah, so a fraction of a percent, right? On Mars, it's 96% carbon dioxide, a little bit of neutral gases like argon, and a little bit of nitrogen, trace amounts of oxygen and water. So it's not something that you would be able to breathe for very long before you would pass out and die. So really nasty atmosphere. Like I said, the last thing I want to say about this is that we do see evidence of methane, and the methane seems to be varying by season. And that's a really, really intriguing aspect, because on Earth we might associate that with bacteria or something like that. There is a process by which rocks can interact with carbon dioxide and produce methane called serpentinization. We have all this serpentine actually out here in Oregon. If you go out, let's see, more towards Cave Junction, there's a ton of these serpentine rocks, very beautiful green rocks, and they produce methane actually in the process of making those. So there is a way to do it. Now, I wanted to mention this one really interesting experiment that people did. One of the first, I believe it was the Viking in the 70s, they had this experiment. What they would do is they had some sort of, it was controlled. So in some sense, what they did was they had a vial, and the vial would basically, when life metabolizes things, right? Let's say when we breathe things, we change the products, right? So we change the oxygen with our body through respiration. We sort of remake it and remodel it, and we breathe out carbon dioxide and water, right? So there's these metabolic processes that result in the change of one product into another. And so the idea was that if there's anything living on Earth, what we should be able to do is take some initial products, put them in a jar, put some Martian soil into that jar, close the lid, and see if they change in this predictable fashion. And we'll, of course, control it because we'll have another jar full of, that won't have the Martian soil in it. And we will see if the products change and compare it to that. And the interesting thing is that they called this the labeled release experiment. And what they did see was a pretty drastic conversion of these products that indicated some sort of metabolic process was going on. They only did that experiment once, and people in the last 50 years have been arguing about what it means. And so, you can read, if you want to read more about that, I don't have time to get into the details of it, but there's arguments on both sides about what could have caused those metabolic equivalent reactions to unfold in the absence of life. But there's still a few holdouts. There's a couple of guys at NASA, some of the really old dogs that were around at the time. I don't know if they're there anymore, but very recently they were there, and there was a few characters who were holding out that, this definitely means there's something biotic living on Mars, for sure. So, jury's still out. I would say that most people probably try to explain that away in terms of abiotic processes, but it's a tantalizing experiment and tantalizing piece of evidence. All right. The last thing I want to say about Mars is that this is a picture. We can actually see its atmosphere being blown away to this day. It's losing its atmosphere very, very quick. And there probably won't be much of it left after another few million years. This is a picture. Let's see what we have over here. We see atmospheric carbon, oxygen, and hydrogen. The hydrogen is being blown away at an extremely fast rate. Of course, hydrogen is the lightest of those elements, so it's going to be the first to go. All right, I think I want to put a pin in Mars and spend the last few minutes here talking about moving outward. Does anybody have any Mars questions? Yeah.
For the moons, you said that one of them was on the path of trajectory to fly off, and the other was looking like it's having impact.
That's right, yeah.
That's probably like millions of years off.
Yeah, I don't know what the timetable is on that. Yeah. Maybe somebody can Google that and tell us. I'm not sure. I think that it's millions of years is pretty fast in geological terms, so yeah, I would guess that it's on that order. I mean, our moon, by the way, our moon is leaving too. Nothing to be concerned about. I think it's leaving on the order of centimeters per year, which, I don't know, there's interesting debates again about whether that matters at all. Like, will we miss it? The gentleman I was talking to, I remember his last name now, Sean Raymond. He's at the University of Bordeaux in France. he was saying, yeah, it doesn't really matter. The moon can go away. Like, we won't have tides anymore, but who cares? But there's other people, like when I was talking about the importance of potentially the moon on churning the interior of the Earth at the end of the last class. You know, I actually asked him about that, and he wasn't aware of that study, and he was like, yeah, I don't know. It seems like we'll have plenty of motion just from the Coriolis forces and the spinning of the Earth and so forth. So maybe it matters, maybe it doesn't. It's hard to say. It will be certainly a sad day to see it go. And who knows, you know, the loss of that amount of mass from our dyad system, will that perturb our orbit in any way? Will the moon flying off into the solar system join somebody else's planet or throw them off of their orbit? You know, there's actually this very real concern that as we explore these different bodies, you know, for instance, every time that we try to go out to Neptune or someplace really far away, Pluto, that we slingshot around these planets on the way out. We get a little bit of momentum from them, so we don't have to burn our thrusters as much. We just lock into the gravitation and then kick off of it. And we get a little bit of momentum from that. But we also mess up the orbit of those planets just a tiny, tiny bit every time we do that. Now, it's very insignificant, but what if a moon did that? You know, it might be very significant. And of course, if you change the orbit of Jupiter, everybody else is going to follow because everybody's in some sort of orbital resonance with Jupiter. It's definitely got the most mass other than the sun by a long shot in the whole solar system. So you change one piece, maybe you change all the pieces. It's kind of the butterfly effect thing where, you know, a tiny little effect in one place can really change the world overall. And I think that's true. It's very true. I think that you'd be surprised how much you can change the world just by smiling at people every day. It's the tiniest little things really do seem to ripple. And it seems to be the case on the astronomical scale as well. Did anybody get a chance to see when we're going to lose those Martian moons? I know somebody's got Google. Everybody's got laptops out here. Somebody please figure this out. Tell me when you got it. Any other Mars points? Yeah, Google it. Okay, let's start talking about the giant planets. So we're going to skip over the asteroid belt. So in between these rocky planets, the terrestrials we've been talking about, there's a big field of debris, and we're going to come back to it. I think we're going to do asteroids and comets in one lecture. I don't remember when, but we'll get to it. We'll get back to them. We're going to move past that, and we're going pretty far away out to Jupiter and Saturn and Uranus and Neptune. These are generally considered the giant planets, and we'll see exactly why they're called giant in just a moment. They're very, 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 very different than the ones we've been talking about so far. They were originally considered, they called them gas giants because they considered them to be primarily comprised of gas. It seems more adequate to call them liquid planets or something like that, liquid giants, or ice giants in the case of Uranus and Neptune, because in some sense there's no real surface on these things like you would expect, right? On a terrestrial planet, you can't exactly land on them because you just get into, the closer you get down into them, let's say beyond their apparent surface, where we would say the visible surface, you go down into that, it just gets thicker and thicker. The atmosphere just becomes thicker, becomes liquidous. At some point it becomes really, really high density. You get this metallic hydrogen, and in some cases at the cores of these you get rocky bodies, which is really, really interesting because at the cores of something like Neptune, you get something that's rocky, almost like the planets we've been talking about so far. Very, very similar in composition, which is, we'll get back to how interesting that is later. But the first thing that we got to understand is the delineation between these giant planets and like Jupiter and stars, because they're not as different as you might think, which is really interesting. So a gas giant or a giant planet, let's say like Saturn or Jupiter, is primarily composed of hydrogen and helium. So are stars. Okay, so they're made out of the same stuff. It's reasonable in some sense to treat them as failed stars because in some sense they really are the same material thing. They're just not big enough to crush themselves in a way that they're able to do fusion. Right? And fusion seems to be what gives the sun all of its, particular attributes, this insane solar wind and radiation. It has all of this outward pressure because of these fusion reactions. And so they really are an interesting missing link. Now, previously, like honestly, if I would have been teaching, even last year when I was teaching this course, this is how fast things are changing. The overwhelming idea would have been that, well, it's still probably the predominant view, but there's some interesting contrary evidence now. We would have almost certainly had to consider that Jupiter-like planets would have formed inside of a solar system during the process of solar system formation. But what's really cool is with this new James Webb Telescope, we've actually started to see pairs of Jupiters orbiting each other without any star whatsoever in the Orion Nebula. Not just like one or two of them, but like dozens of these things. And so the question starts to become, do these giant planets have the ability to form without a solar system, much the same way that a star would form, by this kind of aggregation of a little seed that starts to pick up material around it and get swirling in an interesting way so as to form a star. And of course, it is reasonable to think that these Jupiters did have something like a planet, like a disk around them, much like a solar system would have in its early days, right? The formation models for these Jupiters involve a similar disk as well. And so are these, in some cases at least, do these Jupiter-like planets form very much like they're gonna be a star, but they just don't get enough material to do it? The difference between, say, these gas, what we would have formerly called gas giants, I think it's reasonable. They're gonna probably keep calling them gas giants, even though they're not gas. There's also these ice giants, which are very similar, except their composition is a bit different. So instead of just having hydrogen and helium, which they do have, they also have heavy things like oxygen, carbon, nitrogen, sulfur. And we got two of those, Uranus and Neptune, and we'll get to those, I think, probably next class. And then there's these really, really interesting things that we don't have. We don't have any. They're called brown dwarfs, and they're bigger than Jupiters, but and they do fuse, by the way. They fuse heavy versions of hydrogen. So they'll take these hydrogens that have extra neutrons, these isotopes, and they can fuse those. But they can't fuse regular old hydrogen like a star. And so that's the only difference. It's this interesting continuum, right, where you have Jupiters, you have brown dwarfs, and then you have stars. And the crumbling boundary between that just really seems to be how much material you can get in one place at a given time. And so in some sense, these are kind of my favorite planets in the solar system to talk about because I think that there's such a crumbling boundary between a star and a planet when we start talking about these giants, right? It's like they could have been their own star system if things would have gone a little differently, maybe, right? And then, of course, you have to ask yourself, okay, if there's a threshold of material, right? So, in other words, to become a brown dwarf, you need a little bit more material, right? Same stuff, hydrogen, helium, but you need a little bit more of it in order to start fusing that heavy hydrogen, that deuterium. Well, at some point, there has to be a line drawn in the sand where you have enough material. And that's like the difference of one atom at the end of the day, right? At some point, you get that one extra atom, boom, now you have the mass to start doing fusion of heavy hydrogen, that deuterium. And then again, that brown dwarf can get pretty big, but it can't do fusion of regular hydrogen. But at some point, there's literally a point where you add one more atom and boom, it's cooking like a star all of a sudden. And so you have to really open up your imagination to like the reverse pathway of that. Is it possible that there are stars that if they lose one atom, now they're a brown dwarf all of a sudden? Is it possible that there's a brown dwarf, if it loses one atom, now it's a Jupiter all of a sudden, Jupiter-sized planet? It's really interesting to imagine that process could go both ways. And I don't think anybody's ever seen that happen, but it seems, following from first principles, that it's absolutely possible and almost, seems probable in some sense to me. So that brings in this, there's this other really interesting thing you might want to look into called the VASCO project, which I think stands for Vanishing, I can't remember it. It's basically like these vanishing stars that people have been cataloging. So somebody went back through all of these defense projects. There was this Defense Department survey of the skies. They were trying to, I think they were trying to track Soviet satellites. basically. But they also ended up making this long catalog across many years of the same window of the sky. And what they noticed was that there was a lot of stars that just disappeared. Very, very strange. And of course, they were able to account for some of them. Maybe this wasn't actually a star in the first place. Maybe it was something else. Maybe it was, just like a nebula. Maybe they were able to explain away a good chunk of these. But there was a big chunk of them that they weren't able to explain away. And they're interesting mysteries that still remain. So do stars just blink out? Does that happen sometimes? In some sense, they saw stars appear that weren't there before. That some of them even disappeared for a little bit and came back. So, I actually talked to I had the privilege of sitting down with the director of that study at one point last year. You can check out that conversation if you want. But, she was very, very hesitant to speculate on the mechanism. She was just like, look, I'm just cataloging these things. I don't want to mess with why that is. But, if you consider this thing that I'm telling you about the crumbling difference between Jupiters, brown dwarfs, stars, they're really, really on a continuum together. And I think that there's an interesting cause for mechanism of how these stars could really be quite transient at some level. I don't think most stars are like that. Most stars are enormous. Most stars are not. Actually, most stars are not bigger than our own sun. But still, our sun's enormous compared to a brown dwarf or a Jupiter. But I think that this coming and going of starhood, let's say, seems to be a reasonable possibility at least. Although, other than the Vasco project, I don't think anyone's ever seen it. Okay, cool. So let's define these things really quickly, just in case we haven't already. So the gas giant is what they're going to call these things in your textbook. They're primarily comprised of hydrogen and helium, just like everybody else, but they're below some threshold. The brown dwarfs are just extra large. They're bigger than 12 Jupiter masses. And actually, that boundary keeps changing. They've rewritten that boundary a few times. So, but for now, greater than 12 Jupiter masses. And then the ice giants are similar, but they also are composed of elements that are much heavier than a gas giant. So they end up having a lot of these volatile liquids and ices and so forth. So let's look at these brown dwarfs. Here's kind of an interesting representation of them. So because they're able to fuse deuterium, they're warm. So we can see these things within the infrared spectrum when we turn our telescopes out towards them, which is, makes them in some sense one of the more easy bodies to detect. It brings up this interesting idea that oftentimes these brown dwarfs are found without a solar system too. And how did that happen? Well, in some sense, I think the most popular idea is that they're failed stars. Like I was saying, they were on their way to becoming a solar system themselves, but they weren't able to pull it off. There's been wild speculation about how many of these free-floating planets there are in between stars, right? The estimates have been really, really high, like as high as several per solar system, down to something like one per solar system. The problem is that most planets are cold, especially if they're not orbiting a star. So you can't see things that are cold very easily, particularly if they're small and rocky, right? They're not going to lens the light in a nice, easy way. In fact, when we were talking about exoplanets, the ones that we're able to detect are the big ones that are closest to the stars because they make those nice shadows in front of them. And there's other ways that you can look at the way the light is sort of lensed around them, but the smaller it is, the denser it is, the colder it is, the more difficult it's going to be to detect. So there might be a lot of stuff floating out there in interstellar space, a lot of planets that for whatever reason got kicked out of their solar system, or maybe like these brown dwarfs never actually managed to establish their own solar system in the first place. They're really, really interesting bodies. Let's skip over that. So, they call them brown dwarfs, but despite that, their color actually depends on their temperature, just like a star. So the hotter, just like a burning coal or something, right? The color of stars really comes down to their black body profile. And black body is just kind of a scientific way of saying the color spectrum that you get by heating up something. So like, these are gas lamps, but if we had an incandescent light bulb, it's going to have a particular temperature profile. Sometimes you see that at the store when you go to buy light bulbs because you want it to have a warm glow or something, right? So all solid and liquid bodies do that. When you heat them, their thermal radiation gives a profile where the color can tell you about the temperature. And so brown dwarfs are no different. So the warmest ones are kind of orangish red, and the cooler ones appear kind of magenta or even black. Just you can't see them at all with the visible light. An interesting thing that kind of separates them from Jupiter's, these brown dwarfs, is that they're fully convective. So they don't have, as you penetrate down with your wavelengths. So remember, you can dig down through gases with radiation like radio waves and so forth, and radar, right? We talked about that with Venus imaging the surface. As you dig down into these things, you don't see these different layers of differentiation. There's not. Do you guys remember when we were talking? I showed you that cool module called nullschool.net where you can see the different layers of Earth's atmosphere. So Earth has these really, really interesting different layers, and some of them are marked by convection. There's different currents going in different directions. It's really quite intricate. And you don't see those on brown dwarfs. And you don't really see those on the sun either. So it seems like that, in some sense, puts them closer towards the star end. Whereas on Jupiter, we'll see that we actually get very different convective layers as we dig down into the surface. All right. So the nearest brown dwarf to us is something like 6.5 light years away, which is a bit tragic that we don't have anything quite near to us. This is in the third closest system to us after Alpha Centauri. All right, what else do we want to say? One thing that's really interesting, these seem to be enriched for lithium, which makes them different than low-mass stars, which could be confused. A lot of the stars in the sky are very small M-class stars. They're smaller than our star, and some of them are very cool. And this makes them very difficult to see. So most of the stars in the sky are not visible because they're very, very cool compared to our star. And brown dwarfs can get thrown into this mix. So people try to separate the brown dwarfs out from the stars by the presence of lithium, which is quite interesting because in some sense, where do they get all that lithium from? Lithium is a product of fusion. So, maybe it speaks to their past. Maybe at some point there was that sort of fusion going on and now there isn't anymore. I don't know. It's very interesting. Lithium gets burnt up the older a star is. So when a star has gone through its lifetime, it sort of uses up that lithium. So let's compare the cross-section of these things a little bit here in the last few minutes. This is a brown dwarf over here on the left. And so and then we have a Jupiter, and then we have our gas giants. These are from other solar systems. Then we have Saturn and Uranus and Neptune. The molecular hydrogen is like the gaseous hydrogen. So you can see on the brown dwarf, there's very little of that gaseous hydrogen, right? Most of the hydrogen is in this metallic form, which is really, really fascinating. Because in some sense, I hope some of you will stick around to take the course next semester because we're going to be talking a lot about what stars are, right? Because traditionally in the last 100 years, we've modeled stars as gaseous bodies, right? You've probably heard the sort of trope that the star is a burning ball of gas, right? But this is a tricky proposition in some sense because, in particular, like I said, with the incandescent light bulbs, right? Solids and liquids that you heat up, they give that very beautiful continuous rainbow of frequencies. Well, the sun does also. The sun behaves, it gives the light this beautiful black body spectrum that in some sense is identical to what you would see from a light bulb or any glowing iron or something like that. Whereas gases give off, if I was to put a spectrum up to, you could try it sometime. If you hold a spectrum up to these lamps, you're going to see individual lines of color from these gases, right? Now, the sun has an atmosphere, and so, of course, do these brown dwarfs. They have a little bit of a thin atmosphere of hydrogen gas. But the overwhelming majority of them are treated as metallic hydrogen, which is really interesting. It's kind of this conductive form of condensed hydrogen, which would be capable of giving a black body spectrum, and that would make a lot more sense in some manner of speaking. So we'll unpack that. It's a really interesting frontier of stellar material science right now. I've had a number of really, really almost contentious conversations with astronomers about the material basis of the sun because in some sense the argument that the sun is a gaseous plasma of some sort is severely contradicted by some experiment every single person can do right now if they take a prism outside and look at the sun.
You wouldn't think it would have any gravity either if it was this gas.
Well, they say it's a really dense gas. And so then it gets into this strange semantic argument about, because what happens to it, all right, let's say we take a bunch of gas and we compress it into an oxygen tank. What happens? It becomes a liquid. So it comes down to this word plasma, because plasma is one of those nebulous words. It's trying to think of another equally nebulous word that we use all the time. Person or something. I don't know. It means almost nothing. It's so general as to mean almost nothing. Plasma, it seems like, can speak to liquids. It can speak to gases. And so, you'll increasingly see people calling the sun a plasma because I think in some sense they're trying to avoid this contradiction. But anyways, what I want you to take note of is just that all of these bodies seem to be, in some sense, materially similar. They just seem to be very different ratios of these. You see more gas in some versus others. And in some sense, I think that the brown dwarfs, as we know them being very close to stars already, right? If they get a little bit bigger, they turn into stars. Well, their material composition seems to reflect that they also have a much more condensed matter interior to begin with. So, all right, this sets us up, I think, to be able to talk about our own gas giants next time. And we will start to explore the story of Jupiter and Saturn. So have a great week, and I'll see you guys on Thursday. And come early if you want on Thursday. We'll have some coffee. We can hang out.